All right. Does everybody hear me upstairs? Okay. So very welcome to today's Vinn Explore event. It's great to see so much people. It's going to be a great presentation, I'm sure. My name is Hampus Nestenborg, and I'm the CEO of Hjalta. Hjalta is one of 14 companies within the Vinn Group startup platform. At Hjalta, we help our customers architect, implement, and develop capabilities in a digital landscape. And if anyone here is curious about Hjalta or Vinn Group, just reach out to me or another Vinn employee after the keynote. So as fellow architects and general nerds, we're really delighted to welcome today's speaker. He has, from a technical perspective, played a great part in what is one of Sweden's greatest success stories, I would say. So please give a warm welcome to the Chief Architect at Spotify, Niklas Gustafsson.
Can you hear me? Yep. Thank you very much. Thanks for having me, and awesome to see so many people. As Hampus said, my name is Niklas. I've been at Spotify for a fairly long time. I'm based here in our office in Gothenburg, but I work with all our engineers. So I spend a lot of time in our other offices as well. Today I'm going to try to talk us through a little bit of how Spotify thinks about our organization architecture and how those two are connected. And I'm going to do this through an example of how our backend architecture works. So it's going to start out a little bit around our thinking, and then like how does that turn into our architecture, or how does those two support each other. So Spotify for those that haven't used it is music streaming service. We aim basically to provide audio streaming with the same type of feeling that you would have if you would have the entire catalog of music and podcast locally on your device. And this comes with a lot of constraints on how we need to architecture and build our solutions. We've been, since I started and since day one, always been growing quickly as a company, both in terms of users and size and whatnot. I'm going to talk through a little bit what that means. I'm going to add a sort of a standard caveat to this. So what I'm going to say today and speak about today is something that we've optimized for our company. We published some of that previously, and we've seen a fair amount of like copy pasting of the way that we work. That's fun and all, but it's not necessarily the best model for any company. So be aware of that, and of course be inspired or pick and choose the pieces that might function in your company, but the straight up copy pasting is not necessarily the best way to approach it. Also, much of the stuff that we published is now actually pretty old. But I'm happy to go into that if you have any questions afterwards. I'm going to try to save some time towards the end for questions, by the way. But if there's any questions during the meantime and you feel that you want something clarified, just raise your voice. Cool. So a lot of this talk is going to be around scale. Why you need to work differently at scale. And to exemplify scale a little bit, I'm going to talk through a few different aspects of it. So the first one is 200 million, which is the rough amount of active users that we have. When I started, it was a few single-digit number of users, and I remember starting like on the very day that I started, there was a workshop to design our user registration system to support 100 million accounts, which I thought was completely ridiculous at the time. Like that's insane. We will never reach that scale. We're now way past that scale, which has been an interesting journey. So this is interesting from like a size perspective. So like when it comes to the data sets that we have, storing stuff in a database turns interesting once you have 3 billion playlists. Dealing with our audio catalog turns interesting when you have petabytes and petabytes of data and so on. Next is scale. So we peak somewhere north of 40 million connected clients. And at any given point in time, there will be tens of millions of users connected and using Spotify. And we get somewhere around 5 million requests per second to our perimeter. And then that fans out into many tens of millions of requests per second that our backend handles. So this is interesting from a scale perspective. Like when you want to design your systems to support this amount of scale, you need to think differently about your systems. And lastly, around complexity. So we're now, I don't actually know if this number is fully correct, but we're roughly around 1,400 engineers. And I have no idea, but I think somewhere in between 250 and 300 engineering teams. The fact that I don't know is interesting in itself because there's no like canonical source for which teams exists, and we keep growing them and splitting and reorganizing our teams all the time. So making our org and architecture work from scaling from when Spotify started with 7 engineers to 1,400 engineers has been an interesting journey, and we intend to continue grow. So of course this will continue to be a challenge for us. But even at this scale, we're now a fairly large company. But even if at this scale, we're up against competition of much larger companies and much more established companies. And the fundamental belief that we've had basically since day one is that the thing that we can compete on is speed. We can aim to be faster than those companies. So what I'm going to talk about today is largely like how do you... That's an incredibly shitty picture. Sorry about that. It's from Space Jams, for those that haven't seen it. So I'm going to talk a little bit about how we think about our org structure to optimize that for speed, and how, again, that turns into architecture. So viewing Spotify as a system, with any concurrent system, you want to minimize locking. And that's exactly what we've tried to achieve as well. So we've set up our org to be as autonomous as possible. So you can think about like we have a fairly traditional like hierarchical org structure. And at any level of that, we try to set up the teams to be as autonomous as possible. So that comes with giving a team a clear mission. And I'm going to talk around our search feature today. So you can imagine being a search team that owns search functionality end to end. So they will own building that functionality on clients, they will own the backend systems, they will own whatever data pipelines they need, whatever machine learning models they need, all of that within a team or maybe split into 2 teams and so on. But it's this like well-defined mission to allow that team to execute on their own. And with that mission comes also trying to minimize the dependencies that team will have. So again, they're fully set up in terms of the engineers they need, so they're not dependent on other teams or other parts of the org to be able to build the stuff they think they need to build the best search functionality. And for us, this is really a way of rather than trying to get away from Conways Law. So Conways Law, for those that aren't familiar, is this law that was stipulated by Melvin Conway in the 60s around basically an organization is constrained to design systems that reflects the organization. So you're going to get the same silos in your systems or in your architecture as your org. And this has always been considered to be an anti-pattern. You don't want your systems to reflect whatever org you happen to have at the time. So the way that we thought about this is rather the other way around. We want these 2 things to support each other. We want to be able to have an organization that fits well with our architecture, and the other way around. And you can have an interesting discussion over beers if our org came out of our architecture or if our architecture came out of our org, but I don't think in the end it doesn't actually matter that much. The important aspect is that they function together. And then turning into the example of our backend services. And again, this is just an example. If you would look into our data processing or the way our clients works or the way our machine learning works, it's the same type of pattern that repeats. But in our backend services, this means using this pattern of microservices. And we've been using this for a long time now, 12 or so years. So microservices has never been a word that we've been using heavily because it's a fairly new word, but looking at the definitions of it, we're very much aligned with what the definition of a microservice architecture would be. And for us, that means rather than building like a large system, we build tons of small services. Again, I don't know the exact number, but we have somewhere above 1,500 services in production, different services, running across tens of thousands of servers. And we add roughly one new service into production per day. So the thing with these is that given that they're fairly small, they can be owned by a single team. So a team can own the full life cycle of a service to support the functionality that they need. And given my role of trying to like make sure their architecture makes sense, there's no way for me to keep up with the speed at which we build new stuff. So the intention is all the time that teams can come up with the product they want to build, design the solution for that, implement it and run it on themselves. No one needs to have any insights into what they're doing. That's what we're trying to optimize for. Obviously, we have some larger strategies and we have larger patterns that filters or that feeds into that. But again, end of the day, the idea is that the team can do this on their own. And when I say team, by the way, this is like a standard agile-sized team, so 7 to 10-ish people, depending. And this allows us to decouple the org, again, making sure that teams don't strongly depend on other teams. And one of the interesting parts about this, again, is that given you build and run your own system, you're also free to deploy that as you want. And we currently deploy somewhere around 600 times per day. So that means that every 2 minutes there's a new Spotify version, if you like, of Spotify running in production. And there's no coordination of how that happens. So this allows us to build these, and I'm sure this is going to work as well as the previous one, Seinfeld reference. So this allows us to build this enormously complex system that no one understands from hundreds of small components that is very easy to understand, right? So as an engineer, I can work with a system and it's small enough that I can keep all of that sort of paged into my brain at the same time. And I can think about that system in almost complete isolation from the other thousands of systems out there. Which makes it much, much easier to work with as an engineer. But the whole system is, again, enormously complex. I once prided myself of having like a decent understanding of how Spotify worked. But now there's entire like large systems that I didn't even know existed. The last few days I've been, for random purposes, been reviewing a lot of code, and like you just keep discovering these things that people have worked on that you had no idea existed, which is an interesting experience. So another nice aspect of this is that you can achieve a different level of robustness in your system. Again, if a service is easy to reason about, that also means that once it fails, it's much easier to debug and understand why the hell did it break. Also, when it breaks, it limits the impact of the thing breaking. So again, if our search service or one of our search services would fail, that might mean that searching on Spotify wouldn't work for some time, but playback will continue working, playlisting will continue working, the apps that we give to our artists will continue working, and so on. And this is very important for us, because again, given you do 600 deployments a day, things will break all the time, and you have tens of thousands of servers, things will break all the time. You have to assume that as part of your architecture. And lastly, of these different aspects that we achieve through this is around scalability. And again, if you have services that have a single purpose, that means that you can scale them and think about how to scale them without having to make compromises. So if you have two different things with very different traffic patterns. So for example, for us, we have our playlist service, which stores the 3 billion playlists and serves those to users and makes sure the user can update their playlists. But then we want to serve the pictures for those playlists. And that turns out to be a very different thing. So we opted to put that in a completely different service. So that just basically serves the URIs for pictures, which seems like a stupid thing to do. But that thing gets thousands of requests per second, and with a very different traffic pattern from the playlist service. So being able to scale those two independently is a very nice property to have. So I've been talking a lot about services, just very quickly what we actually mean by a service. So service is something that runs, a process that runs in production, exposes an API over a network. That API is the interesting thing. So others will depend on your API. So you need to make sure that API is stable over time. And we still support clients that are 10 years old that can still play music on Spotify. So that's a lot of API stability to think about. But it also means that we can switch out the implementation. So we have many cases where we have either replaced an implementation because the old one didn't work anymore for scalability reasons, or it had accumulated tech debt over time, or whatever it might be. Or where we need to inject a different type of functionality. And we can do that sort of in runtime, if you like, by adding in something that provides the same API so that the users of that API will never notice. So the way that our service discovery and the way that our dependencies in between services function, they're only dependent on a service name and an API. And everything else we can change as we like. Again, very quickly on the tech stack that we use. If you have questions afterwards, feel free. We provide a minimum set of strong guidelines, like you need to use Java. That's our main language if you're in the user request path for scalability reasons. We want teams to, as we say, move up the stack. So we don't want teams to focus on the low-level infrastructure. We want to use whatever infrastructure we can find out there. So that's historically been us using a lot of open source tooling. And over the last few years, we moved into Google's cloud solution so we can leverage the products that Google built for us. So instead of having, like we did before, teams that were building data centers and racking servers, we can now build on top of the infrastructure that Google builds for us. And this is a continuous thing that we want to do. We always want to be moving up the stack, operating at a higher and higher abstraction level. And then we, at times, need to build custom or proprietary things. So that's either when we scale out of a solution, which has been the common pattern for us, or when there's something that is very custom to what you need for music streaming. And that's been a fairly common pattern as well. But it's besides that, we want to be on a pretty standard platform using the sort of boring, stable technology that already exists. So to illustrate how our services architecture works in a little bit more in practice, I'm going to trace us through like what happens with a single request that comes from one of our clients. And this is just an example. This is a typical traffic pattern we have, but there's more. Like we do publish, subscribe, we do stream-based processing as well, for example. But in this case, we're going to look through what happens with pretty typical thing when a user does something in one of our clients. And specifically for this case, we're going to look at that search example again. So the C's in this diagram is a bunch of clients connected to what we call a perimeter service. So this is a service that sits on the perimeter of our backend. It's exposed towards the internet and all the evil things that exist on the internet. And it provides sort of a safe haven for our internal services. So there's very few of these external services, but they take an enormous amount of traffic and they take an enormous amount of hardening from a security perspective. So that's why we want to have few of these, because they're a big investment, but they provide a lot of functionality for the rest of the infrastructure. So in this case, this is exemplified by a service called the access point, which is something we've had since forever, and that we're now slowly trying to kill and replace with a new perimeter service. But it doesn't matter for this example. So now we imagine that a user searches for their favorite artist, which happens to be LJ in this case. So they type in that thing in the search box in their, whatever this is, iOS device. That client will send that request to our perimeter. You can imagine this being a standard like HTTP request. So it happens for the access point that this is a weird shit proprietary protocol. That's why we're trying to kill it, or one of the reasons why we're trying to kill it. But we're moving towards like standard HTTP request. So the first thing that will happen, and this is not enforced, but it's by far the most common pattern that we have, is that this request, it gets routed by this access point, which like looks at the request and figures out that this is a search request. It should go to this thing that exposes a search API. So I'm going to send it to that. That turns out to be a service called Search View. And this service is basically optimized to provide data for clients. And we're going to see on the next few slides a few different type or a different type of service as well. But this is the one that is optimized for the needs of the client. So you can think of this as a one-to-one representation of what you would see in the user interface of our client. So for the search example, this will get the search query and return back a representation that is basically, again, one-to-one to what you see in the client. In some cases, actually, exactly one-to-one, because we will send an entire view state back to the client, which actually happens to be the case with this particular example. But the search view service can't search. It only provides this representation to the client. It's completely stateless. And the purpose, again, is to separate like the client aspect from whatever other aspects we need to care about. And one of the main other aspects is to actually be able to provide search functionality. So we have a service called Search. This has been around since forever. I think it's 10 years old or so by now. It's been heavily modified, of course, over the years, but the same basic code base is there. And this is the thing that does the searching for you. So if you're familiar with stuff like Lucene or Elasticsearch or Solar, things like that, that's basically what this thing is doing. The users have used Lucene over the years. This was our first service written in Java because we needed Lucene. So this was like the exception that we hated and then turned into why we actually switched to using Java everywhere, because Python that we used before didn't scale. It has states. It has some sort of database, like a Lucene index. Now we're switching it to Elasticsearch. And this is the thing that, again, provides the actual search results. So this contains our entire catalog. And if you search for Alt-J, you're going to get back a bunch of identifiers identifying whatever content we have for Alt-J. But it only returns those identifiers. We need to decorate that as well. Or the thing that we want to show for our users is not a long list of UIDs, because that wouldn't be super useful to the user. So we need to decorate this with what we call metadata. So that's, again, where this Search View service now is orchestrating a bunch of requests to different backend services to, again, provide the thing that the client needs. So one of those backend services that we'll be heavily using is a service called Metadata. And this contains all the data for our catalog. So it contains, for a track, what's the artist, what's the duration of the track, what's the genre for the track, and so on. So the Search View service will send all of these identifiers that it got back from the search, have them decorated by the metadata service, and then provide that back to the client. And this is a super simplified example. In reality, the Search View service will actually fan out to, I think, roughly 15 different backend services to provide all the content that is needed for a single search request. And again, this gets lots and lots of search requests per second. It's also highly simplified in that this is now a personalized result. So the result that comes back to the Search View service will actually be ranked by a machine learning model that is trained on every user's personalized taste. So there's, in this picture, should be something called Search Rank, which is a different service which does exactly that. Given a search result, these are the things that I prefer when I would search for Alt-J. Maybe not that interesting in this example, but if you search for like pop music before ranking, you wouldn't get very meaningful results, but now we can actually return the results that make sense for you. All right, so this is all nice, and like this is, again, a very simplified, but a pretty standard way that a request that goes through the Spotify backend works. So now I wanted to talk a little bit about how we need to scale this out. So you can imagine that for this search service, that actually runs on lots and lots and lots of servers, because it gets, I don't know what the actual number is, but I would guess like hundreds of thousands of requests per second probably, or tens of thousands at least. So the way that we thought about this is basically like the simpler we can make the services, the easier it is to think about how to scale them linearly. And historically, not so much anymore, but historically we've been heavy users of static indexes over your traditional database. Because the nice thing with static indexes is that you can scale your instances completely linear. Adding another, if you have one instance, adding the second instance give you exactly twice the amount of performance because you have no shared state in between those two instances, right? They have their own immutable index on the instance where you run it. So this is the way that we've used Lucene indexes, for example. It has some pretty significant downsides in terms of making updates quickly to your data. So that's why we're moving away from it, but it's been a very useful pattern for us to be able to scale out. And it's incredibly hard to replicate when you have a shared database. So we've been heavy users of Apache Cassandra over the years, which have the sort of same property of like horizontal scalability. But for things like Elasticsearch, for example, it's actually pretty hard to scale that to high volumes. But scaling out also comes with being resilient towards large-scale failures, and also to be closer to users. So in addition to this, we will also run a complete clone of our backend in multiple locations around the world. So we're currently in 3 locations. We've been in everything from 2 to 7 and now back to 3 different locations, depending on various changes that we've done. And we want to have these placed so that they are both isolated from each other as much as possible, and also as close to our users as possible. And we now have users all around the world, of course. So we have capacity here in Europe, we have capacity in the US, and we have capacity in Taiwan to serve our APAC region. And one of the nice ways that we've been able to do this is that we've been focusing on make sure that we can replicate on the storage layer. So again, when using Cassandra, Cassandra is nice because it provides that replication for you. You can basically have a storage cluster in the US and a storage cluster in EU. You can read and write to those 2 storages, and Cassandra will provide replication and conflict management for you under the hood. So from a service developer perspective, I can have my service that runs in the US that works with my storage cluster that is also in the US, and that's all I need to think about. And then I can look at the same service deployed in EU towards a storage cluster deployed in EU, have the same thinking. I don't have to think about how this is replicated, how this works under the hood. So that's been a very nice property for us and something that we continue using. Having multiple regions also allows us, similar to what I said before with services, to have limited blast radius during incidents. So we've had many occasions where an entire data center has failed. The network has failed, or storage has failed, or we've deployed stuff that breaks something. And then we have the ability to fail users in between our regions. So we will take all the users in EU, move them over to the data centers in the US, for example, for some time period while we repair the data center in EU. And this is actually something that we do repeatedly just to make sure that we can actually move users around freely. And it's been an extremely valuable functionality for us from an availability perspective.
Second. Oh, I didn't know what a billion was. I don't think most of those men downtown know what a billion is either. And if you don't know what a billion is, how on earth do you know what a billionth is?
So sorry, I didn't intend for that to have sound. That was a Grace Hopper, who's one of my personal heroes in the computer science world. She was an admiral in the US Navy and one of the very early computer scientists. And one of the things that she liked to do, and that she does in this video, the video is unfortunately very crappy quality, but what she does in this is to do this demonstration of how far light travels in a nanosecond. And it's this like 30 centimeter piece of string that she uses in this demo. And then given their militaries, they have satellites. So then she does like the extrapolation of that, like imagine how many of these there are up to your satellite, and that will be the latency for your traffic. That's the demo that she does. For us, this means being a Spotify user, even with the 3 data centers or 3 regions that we have capacity in, if you're a Spotify user, say in Australia or in South America or in South Africa, you're pretty far away from our data center, and just having light travel that distance takes quite some time. And we want playback to feel immediate. Like I said in the very beginning, like we want it to feel like you had all that music on your device. And for our estimates, that means that we need to, in between the user clicking on the play button until there's audio coming out of the speakers, that should be below 250 milliseconds. That's for audio. This is very different for video, for a website, and for audio. But for audio, that's the latency that will seem immediate. And 250 milliseconds is not a long time. And during that time, we have a fair amount of work to be done. So we have to figure out what you're trying to play. That sounds pretty easy, but given you can be playing very long playlists, like how should we deal with that? We might not have all the metadata available when you start playback, and tons of other aspects. We need to do that. We need to get the audio file. We need to get the decryption key for that audio file. And all of that in that and then actually start playback and decrypting and start playback, and all of that in 250 milliseconds. And given the distances from users to our data centers, that's actually not physically possible. And we haven't fixed the speed of light yet. So the way that we need to do this is that we need to move our content closer to our users. And the traditional way that you do this is through CDNs, content delivery networks, and we do that as well. Historically, we've used a bunch of other methods. We had our own storage, we had a peer-to-peer solution, and then we moved to CDNs. The CDNs are nice in that they have capacity everywhere. So a CDN provider will typically have servers in hundreds of locations around the world, or if you're one of the big ones, in thousands of locations. It's a problem for us because we have such a large data set. Like we have petabytes of audio, so we can only fit that much audio into those CDNs. They have finite storage, of course. So we do a lot of trickery around this. Like we can store the first few seconds of audio in a CDN. We can do all types of trickery with how we position content in our CDNs. Like we have a control plane that will decide for every track that a user plays where that particular file should be retrieved from. So we can actually control that traffic in very much detail. And that allows us, even in locations, again, that is very far away from our data centers, or locations where connectivity might be limited. So if you're a user in Indonesia or a user in India, your connectivity might not be all that great. Both your last mile, like your mobile connectivity or whatnot, but also the actual infrastructure to get data in and out of that country might be heavily limited. So that means that we want to have our data as close to the users as possible, and preferably like for markets like that in the market. And that's again where CDNs provide that functionality for us. And the way that we can reason about this is through measuring that user experience in a ton of details. So we will know like what's the latency of an individual stream that we do. What's the amount of stutter, like buffering events or interruptions that we see during an individual stream. And then we can optimize our capacity based on that. So if we see that we have crappy latency in the market, we can make sure that we add in capacity in that market, or make sure that we're better connected to a particular ISP where we're seeing worse performance, for example. And we do a lot of work around that. Right, the last topic that I wanted to touch on is operations. So I already mentioned that a team owns their functionality from ideation to product strategy, to design, to implementation and maintenance. So we have this concept called ops in squads. So we used to have a centralized operations team. These videos turns out great. We used to have a centralized operations team that would work as a traditional operations team. You would build your thing, hand it over to someone in the operations team that would run that for you. The problem, of course, was that as we grew and as we added more and more services, the poor people in the operations team could no longer understand all of those services. So what would happen in practice would be that they would escalate it back to you as a developer. Like, your service broke, can you please help me get it back to working? So as a backend developer, I started at Spotify as a backend developer. You were implicitly on call 24/7. I happened to get to own the service that at the time had most traffic, this metadata service that I talked about before, the sort of previous iteration of that. And we had constant incidents for that service every Friday evening for a year. That's where we have peak traffic. That sucks. It sucks even more when you don't have a system for it. So, and again, this didn't scale for us. So the way that we did this is the way that we do everything when we scale, and that is to distribute this out in our teams. So today, as a squad, which is the name of our delivery teams, you run your own services. You are on call for your services. So I will go on call for the services that we build here in Gothenburg. And you have a schedule, and you like organize, so you have on call for a few days where you're like 24/7 responsible for your stuff working, and then you can actually rest for some time because someone else is on call for that. And this creates this very tight and neat feedback loop. So if you write a shitty service that will break all the time, it's you being woken up in the middle of the night. It's not someone else in an operations team. It's you or the person at the table next to you. And this feedback loop, pretty instantly actually for us, created a much higher quality in our services, and we would see less incidents in reality. And it also feed back into the work and the planning you do as a team. So if you have more tech debt in your team, your services works worse, you need to spend more of your development time on making them work better. So you need to free up time to be able to spend that time on the actual product development that you want to do. And that, again, feeds into this like autonomy of the squads and being able to fully own your mission as a team. With that, I'm done, and again, thank you very much for everyone for coming, and I'm more than happy to take questions for a few minutes.